In this video, we'll be covering, again, first derivative test on a polynomial function. This identifies to find all local maxes and local mins. So, in terms of this particular function, the first thing we're going to do for the first derivative test is, again, take the first derivative and find all possible critical points. So I'm going to have 3x squared minus 22x plus 39. In that case, this particular function here is something I'm going to have to factor. So, again, critical points are where the derivative does not exist, or it's, again, the first derivative is equal to 0. You'll notice that this is a polynomial function, which means the does not exist case doesn't have to be worried about. But setting it equal to 0 is what we have to work with. In which case, I'm going to go ahead and set this thing equal to 0, and I'm going to have to attempt to factor this. Now, if we recall, the most appropriate way to factor this is do 3 times 39. And again, over here, I'm going to do my scrap work because I'm a little bit lazy when it comes to this. That's 3, 3, and 13 for all possible factors of these two things together. You'll notice if I'm attempting to get a negative 22, but this has to be a positive 39 times 3, that means if I group these two together, that's going to be a positive 9 times a positive 13. But if I make them both negative, I will end up with a negative 22 for the value I'm looking for. So these are the two numbers that it's going to tear apart into. Again, normally you'd set up a table, and again, 3 times 39, whatever the heck that number happens to be, such that you're adding to get a negative 22. And the numbers would be 9 and 13, such that they're both negative, and that would add to negative 22. So over here, I'm going to tear this thing apart into 3x squared, negative 9x, minus 13x, and then plus 39. Split it down the middle, and out of these two terms, I'll factor out a 3x, and be left with x minus 3. Out of these two terms, factor out a negative 13 and be left with an x minus 3. This gives me 3x minus 13 as one factor and x minus 3 as the other, equaling to 0, which then provides me with x equals to 3 as a critical point and x equals to 13 over 3 as another critical point. So those are my two critical points. Again, once we've identified our critical points, we're going to go ahead and create a number line. Now 13 over 3 is a little bit more than 3, because again it would be 9, 12, it would be a little bit more than 4 actually. So I'm going to have 3, and over here I'm going to have 13 over 3. And again, knowing that this is approximately 4 and some change tells me that my test values that I'm going to want to pick are, well, let's see here. I'll pick 4 in this section, I'll pick 5 in this section, and I'll pick 2 down here. Those are the test values I'm going to work with. Again, I want to know what the derivative function is doing, not what the original function is doing. I'm going to go ahead and identify what the original function is doing based on the derivative function, and then I'm going to want to know what the graph, give or take, is doing based on that information. So, with this being dealt with, I'm going to go ahead and plug in all these values to my derivative function. My derivative function is, again, right here. This is the factored form, and I'm going to work with the factored form because it's generally easier to plug numbers into. If I were to plug 2 to this, it would be 6 minus 13, which ends up being a negative number, and then 2 minus 3, which is also a negative number. Negative times negative ends up being a positive. Do the same thing with 4. We get 12 minus 13 is a negative, but 4 minus 3 is a positive, so it ends up with a negative, and when I plug in 5, it's 15 minus 13, which is a positive, and 5 minus that, which is a positive. So those are the locations of what I have. Therefore, I'm going to have increasing, I'm going to have decreasing, and I'm going to have increasing based on, again, positive derivative is increasing, negative derivative is decreasing. That means I'm going to have a graph that, again, goes up, down, and up. With all this information done, that tells me that the x value of 3 should provide me with a local maximum. Because, again, notice it should curve up, hit a point, and then come back down. And the same thing should happen here. I'm going to curve down and then curve back up. So at x equals 13 over 3, I should actually have a local minimum. So the last thing I need to do to finish up this problem is note that there is a local minimum at x equals 13 over 3 with a value of f of 13 over 3, which again I'll let you go ahead and use that into a calculator, but it's 13 over 3 cubed minus 11 times 13 over 3 squared plus 39 times 13 over 3 minus the 47. Again, whatever that number happens to be, that's what your value of that local minimum is going to be. Your local maximum, on the other hand, is going to be at the value of x equals 3 with a value of, again, it's just simply f of 3, which is equal to, again, in this case, I'm going to do 27, I'll make notes up here, 27 minus 99 plus 27, 3, 9, so 117, I believe, minus 47. Whatever the heck that happens to add up all into, get you a number down here, and I'll let you go ahead and verify that with a calculator. And those will be the two answers we're looking for. Again, the first derivative test allows us to identify increasing and decreasing, utilize the increasing and decreasing to say that there has to be a maximum here, and then there has to be a minimum here, because the way the curve is going to go is going to curve up, and then it's going to curve back up. Okay, it's going to curve down and then back up.